Hello, and welcome back to another engineering problem video. My name is Evan DeMars. If you haven't been to this channel yet, uh, I'm in a little bit different scenery. This is a special holiday uh, video that I'm making. And one of the things I love to do during a holiday is to light fires in the fireplace. So one thing I'm going to be talking about is, let's say you want to use a blowtorch or some sort of lighting mechanism to light your fireplace. And that brings me to the topic of this video, is an adiabatic flame temperature of a steady state system. So let's say we have some sort of system, it could be our blowtorch that we're using, and we have air and fuel coming into the system, and we have an extremely high temperature heat and gas exiting the system as our effluent. So we're going to call this our flame. Let's assume that the temperature coming in to our system is 298 degrees Kelvin, and we're trying to understand the temperature of our flame that's going to be coming out of the system or out of our blowtorch. So to get started with this problem, we need to look at two key components that's given to us in the title. This is adiabatic, and it's also steady state. So we know that the energy or the temperature going into the system is going to equal to the energy and the temperature exiting the system in our effluent. And we also know that because it is steady state, that all of the number of moles in the mass entering the system will equal what's coming out. So in equals out. So to begin, step one, I'm going to set up our energy balance. So I'm going to keep this simple. Let's just say the change in mass of the internal energy plus the kinetic energy plus the potential energy of our system is going to be equal to the change in mass of H plus kinetic energy plus potential energy going into our system minus change in mass of H plus kinetic energy plus potential energy exiting or going out of our system. I'm going to ignore work non-flow for now because I just want to keep this simple. So remember, we know that it's adiabatic and it's steady state. So because of that, we can just cross out potential and kinetic energy. They're not going to form anything within our energy balance, and I'm just going to remove them for now. So we're left with the change in mass, the internal energy of our system is equal to the change in mass H in minus out. Oops. H out. We also know that this is going to be with respect to a certain amount of time of of our air and our fuel going in and then exiting, so it's with respect to time. And we also know that the change in mass of our system is essentially not going to change. The internal energy of our system is not going to change, so we could set this all equal to 0, and we're left with H in minus H out. Or we can say enthalpy coming in is going to be equal to enthalpy coming out. So in the most basic form, I've simplified our energy balance for our system, knowing that it is adiabatic in steady state. So the next step of our problem is that we know that when we're dealing with temperature in a chemical engineering problem or a thermodynamic problem, we need to take into account the specific heat. And we know that the specific heat is a particular unit that corresponds to the compound or molecule that we're working with. So in this point, we know that we have air and we have fuel. So we know that air is about 79% nitrogen, N2, and 21% oxygen, O2. And we're going to have some sort of fuel, and we'll get into that later. But we need to understand specific heat. And we know that this normally corresponds to a direct temperature. So there's a specific heat for a fuel at this temperature of 298 Kelvin, but there's also a specific heat of a gas when it travels to our unknown temperature. So this is going to be some super, super high temperature in Kelvin. And our specific heat isn't going to stay the same from 298 to some high number. So this needs to be a range rather than a single unit. So we're actually going to be taking the integral of this. So what I'm essentially saying here is that if we have the enthalpy of formation for our gas, that's a simplified explanation, but of our gas in this system, And we're taking it first at 298 Kelvin. Erase that for now. And then this is also going to, it's going to increase in temperature to some heat of formation of the same gas at a different temperature of Kelvin. So let's say this is something crazy like 3,000 degrees Kelvin. In order to show this, we're going to be taking the integral of our specific heat with respect to temperature, so dt, and it's going to be starting at our inflow, or our temperature in, of 298 degrees Kelvin, all the way to our temperature T of our outflow. So we're going to have to use this integral within some sort of specific heat equation. And the equation I'm going to be using for our specific heat is going to be as follows. So we're working with our ins and our outs at some specific heat. We need an equation. So I'm going to be taking a CP equation from a very helpful science tool that you can find online, and it's called ChemCAD. And ChemCAD is this huge online database that has integrated a ton of different units and values for different chemicals and compositions that you can look up and find online, so that you don't need to actually go into the lab and formulate these experiments yourself to determine the specific heat equations of our air at different temperatures. So this equation is actually taken from the website. It's called Equation 107, I believe. And it's going to help us relate our specific heat of our air and fuel as it goes from our initial temperature to what we want to find as our final adiabatic flame temperature. So I'm going to write it out here, and I'll show it in the next part of the video as well. It's going to be y equals to A plus B times C over T, temperature, over sine H of C over T squared. And this is going to be plus D times E over temperature over cosine H of E over temperature squared. So here we've set up our 5 different variables, A, B, C, D, and E, which all correspond to a specific compound, so air or our fuel, at varying temperatures. So, for example, so if I can explain that, let's say we have nitrogen, N2, which makes up most of our air that we're using as our inflow, 79%. So the specific heat of our nitrogen is going to be dependent on these variables. So A, B, C, D, and E. These directly correspond to the specific heat of nitrogen as our temperature goes up or down. So we're going to have to take what we just formed here, our integral of specific heat with respect to temperature, and our specific heat equation that we took from our ChemCAD book, and combine them together. So this is going to be a very difficult integration that we're going to be plugging into this equation. So I'm going to be using a program called Wolfram Alpha, which is going to be the next step of this video. So we've already taken our equation 107 from ChemCAD, and I've shown you how it relates to our specific heat that we're going to be using for our adiabatic flame temperature problem. So first I'm going to show you how I got that equation. So ChemCAD equation 107, if you just Google it, it comes up. There's a PDF version of the ChemCAD textbook. Physical properties version 5.5. And if I just search in here and I search equation 107, it takes me down to page 23, and it's right here. So this is what I just showed you on the whiteboard, and it's A plus B plus it's A, B, C, D, and E variables in relation to our specific heat. So now I'm going to plug in that integral from temperature 298 to our unknown temperature into Wolfram Alpha. So Wolfram Alpha is just a very powerful online calculator that's going to help me do these integrals. So if I type in integral, and this is going to be ct over sine h of ct squared. So I'm going to have c over t over sine h, I should put that in parentheses, sine h of c over t. That's going to be squared. And then I want to integrate this with respect to temperature. So it's going to be comma t. Hit enter. Okay, so it's given me, here's our equation, the integral of c over t over sine h of c over t squared with respect to t dt is equal to c cotangent h of c over t plus constant. So that's going to be the first part of our integral. And then the next part, I'm going to do the same exact thing, except now I'm going to be doing the integral of e over t over cosine h of e over t squared. So I'm going to do the same thing. I'm going to keep it the same, e over t, and this is going to be cosine h e over t squared with respect to t. If I hit enter, it'll do the calculation of the integral for me. And I'm left with negative e tangent h of e over t plus constant. So there I've been able to do the integral of the two parts of my equation 107, the c over t over sine h c over t, and the e over t over cosine h e over t. And now I can plug these back into that equation and go back to the board and begin to balance my chemical equations of my inputs and outputs of my system. So now we've used Wolfram Alpha to help us do our complicated integrals, and we've come up with the following. And I've just written it on the board so you remember it's c times cotangent h of c over t for this part of the integral, and negative e times tangent h of e over t for this part of the integral. So now we have our specific heat equation integrated with respect to temperature that we can use later on to determine the final heat of our system. But the last thing we need to do before we take this all in and start coding it and finding an answer is that we need to understand the fuel that we're using for our torch, or whatever we're going to call this system is. So the fuel that we're going to be using is actually a mix of methane, ethane, and N-propane, which are very common fuels used in both real-life applications and in thermodynamic problems. So this is CH4, C2H6, and C3H8. Methane, ethane, and N-propane. So let's discuss a little bit about the chemical reaction that we're actually dealing with here, or the chemical properties or the stoichiometry of these things and what they go through. So we know that we're starting with the air and fuel, and it's going into the system. And we know that for the basis of this problem, we're assuming that air is 79% nitrogen and 21% oxygen. In real life, this isn't the case. There are many other chemicals that make up common air, but for the sake of this problem, we're going to say that they're reacting with nitrogen and oxygen. So plus nitrogen, plus nitrogen, plus nitrogen, and then also plus oxygen. So that is the first step of our chemical process, is that we have our fuels, methane, ethane, and propane, mixing with air of nitrogen and oxygen, and then it's going to react So what happens in a combustion reaction? Well, every engineer should know that when you have a combustion reaction, you're left with heat, CO2, and water. So we're going to have CO2 and H2O. And this is just the basic products of a combustion reaction. And we also still have our nitrogen, which didn't react in the process. So I'll add that in here at the end. So here is our chemical reaction of methane, ethane, and propane mixing with our air of 79% nitrogen and 21% oxygen, combusting within our system to form CO2, water, and nitrogen. So the first step we're going to need to do is that we have to understand the stoichiometry of these equations. We need to know how our fuel is going to react and the amount of moles that we're going to have as a result of that. So we're going to do some balancing of equations, which is everyone's favorite thing to do. So let's start off with methane. We have 1 CH4, so that gives us 1 carbon, 4 hydrogens. So we have 1 carbon over here and 2 oxygens, so I'm going to keep that 1. So now I have 4 hydrogens, and I have 2 hydrogens here with my water, so I'm going to make that 2. And now I have 2 oxygens and 2 oxygens, which is correct, so I'll keep that 1. And with respect to nitrogen and oxygen, I know I have 79% nitrogen versus 21% oxygen, so I'm going to take my nitrogen and do 79 over 21 on my left side and 79 over 21 on my right side. So just double check, 1 carbon, 4 hydrogens, 2 oxygens, 2 oxygens, 79 over 21 nitrogens, and 79 over 21 nitrogens. I'm done with my methane, part of my fuel. This is balanced. So moving on to my ethane, I'm going to do the same thing. I'm going to balance my equation. Start with 1 ethane, which gives me 2 carbons. So over here, I have CO2 and H2O. So I'll do the same thing. If I have 2 carbons here, I want to have 2 carbons here. So I'm going to put a 2 in front of that to have 2 CO2. I have 6 hydrogens. And here, I have 2 hydrogens. So what I'm going to want to do is multiply that by 3. So I have 6 hydrogens here and 6 hydrogens there. But now my oxygens are quite unbalanced. So I have 2 oxygens over here, and I have 4 plus 3, so 7 oxygens over here. So I have 2 here, 7 here. So what I want to do is get this to 7 over 4 oxygens on the left side, which will give me, which will balance my oxygens here, my oxygens here. And now I've upset the balance of 79% and 21%. So I need to take that into consideration, multiply this by 79, so if I multiply my oxygen by 7 over 4, and I need to have this relationship between my nitrogen and my oxygen, I need to multiply by nitrogen by 7 over 4 as well. So 7 over 4 nitrogen, 7 over 4 nitrogen, and then of course my 79 over 21. So 79 over 21 times 7 over 4 nitrogen, and then 79 over 21 times my 7 over 4 nitrogen on my right side. I cannot draw my 7s. There we go. So just double check here. Got my carbons, 2 carbons, 6 hydrogens, 6 hydrogens, 14 over 4 oxygens, and then 4, 6. There we go. Oxygens look good. So now I'm left with just my propanes. Balance the last equation. Almost done. So 1 propane, which is C3H8. So I have 3 carbons on my left side I want 3 carbons on my right side, so I'm going to multiply that by 3. Now I have 8 hydrogens on my left side, but I only have 2 hydrogens on my right side, so I'm going to multiply that by 4. So now I have 8 and 8 hydrogens. Now I need to balance my oxygens, so I have 2 oxygens here. I have 6 plus 4, I have 10 here. So I have 2 here, I have 10 there. Multiply that by 5. And again, I don't want to upset this balance of 79% nitrogen and 21% oxygen. So I'm going to multiply by nitrogens by 5 as well. And then lastly, now that my nitrogens and oxygens are 1 to 1, I can do 79 over 21 for my nitrogen. Oh, that was not good. 79 over 21 for my nitrogens on my left side, and then 79 over 21 for my nitrogens on my right side. Okay, so I understand the stoichiometry of the fuels that I'm putting into my system, and I understand the integrals of my equation 107 for my specific heat. Next step is just to go into the Google Collaboratory and solve for the final temperature of my adiabatic flame. So the last step of our problem in determining the final temperature of the flame exiting the system, the adiabatic flame exiting our system, is we want to import all the different equations that we created into our Google Collaboratory Python and solve for the temperature. So the first step I'm going to be doing, which I've already done, is importing numerical Python, science Python, and tools.che, so because I'm going to be using them later on. One thing I want to focus on is this link here, which I will show you what I'm using that for. This is basically to find all the data and properties of the chemicals that I'm going to be using. So here you can see it has a ton of different chemicals on there, and I'll click on ethane, which is one of the fuels that we'll need. And it shows you just about every calculation you would need to know for ethane. And the one we're mostly going to be focusing on is the ideal heat capacity from, you guessed it, equation number 107 from KenCAD. So if you remember, we go back, this is equation 107. And then from this heat capacity, we can see that it has these coefficients, which directly correspond to A, B, C, D, and E that we used in that equation. One thing I want to note before we go on is that this is actually used in kilomoles per Kelvin, which eventually we're going to have to get back into just moles per Kelvin, but we'll get there when we get there. So the first step is that from all that data, we want to import the specific ones that we need. So I'm going to call this P for the properties of the chemicals that we're going to be using. And this is going to be taken from che.props, and it's going to be all the chemicals that we need within the combustion reaction. So the fuel, the oxygen, the nitrogen, the carbon dioxide, and the water. So it's going to be methane, ethane, N-propane, water, carbon dioxide, carbon dioxide, nitrogen, and oxygen. And I believe that's all the ones we're going to need now. So Shift Enter, I've defined the properties of the chemicals that I'm going to be using. The next step is that I want to define the chemical equation 107 that I used. So remember, I took chemical equation 107, I integrated these two values in brackets using Wolfram alpha so that I could have it as a function of temperature throughout the reaction from 298 degrees Kelvin to the unknown higher temperature of the flame. So I'm going to use those integrations, put them back into the equation, and then write it all out and define it here in my script. So if I define, what am I going to define? Well, this is going to be the change in the enthalpy of my system of an ideal gas. So call this delta H of my system Ig with respect to temperature, because that's what we took the integral for. So return. This is where it gets complicated. So this is going to be from the properties of the specific heat of an ideal gas for A. And it's going to be times temperature plus the from properties specific heat of an ideal gas for B times, and then this is where the integrated form of the equation comes in. So this is going to be P dot CPIG of C, and I believe this is where we used cotangent. So it's going to be 1 over tangent, so it's going to be C over numerical Python of tan H of my P dot CPIG of C over temperature. So that's essentially my cotangent of C over T, or cotangent H of C over T, excuse me. And then it's going to be minus P dot CPIG of D times, and then the numerical Python tangent, it's tangent again, so I'm going to copy and paste this over here, except now instead of C, it's going to be E. And this is going to be P dot CPIG of E times that. So there's my equation that was taken from equation 107, and then I inputted the integrated forms from Wolfram alpha. And remember, the coefficients are in kilomoles Kelvin, so I want to get it to just moles. So here's where I'm going to divide by 1,000. So there we go, it worked. The next step, now that I've defined the equation 107, is now I want to define the enthalpy of the ideal gas in terms of number of moles as well as temperature. So I'm going to define enthalpy of the ideal gas for N comma T. I'll return that. And here's where I'm going to use a numerical Python program called dot, which is the dot array. So if I look that up, np dot, numerical Python dot, it'll explain to us what that is. So dot in Python is a function used to perform the dot product of two arrays. So they're two different dimensional arrays that I'm going to be taking, so number of moles and temperature. So here, N and T, so NP, and then dot array of N, comma, is going to be from our properties dot heat of formation for an ideal gas plus, this is going to be numerical Python of a dot array of N, comma, and then here it's going to be delta enthalpy of the system of an ideal gas, so delta HS Ig, and this is going to be at the final adiabatic flame temperature that we're looking for, minus the delta HSIG of the temperature coming in, so 298. So delta HSIG 298 degrees Kelvin. There we go. So now we've defined that. So we've defined, we've brought in the properties of the different chemicals that we're using. We're also we've also defined the change in enthalpy of the system of the ideal gas by using the equation 107, and then we've also defined the enthalpy of the ideal gas using the dot array function. So the next step that I'm going to want to do is start discussing the fuel aspect of our system. So the methane, the ethane, and the N-propane. The easiest way to do this is actually to turn the different components of the fuel into simply carbons and hydrogens, because methane, ethane, and propane are just carbons and hydrogens, essentially, different numbers of carbons and hydrogens. So I'm going to say that that is fuel of carbons and hydrogens in my equations, and this is going to be equal to a numpy array of the carbons and hydrogens. So for methane, I have 1 carbon, 4 hydrogens. For ethane, I have 2 carbons and 6 hydrogens. And then for N-propane, I have 3 carbons and 8 hydrogens. Okay. Oh, oops. I forgot a bracket. There we go. So basically I've defined my 3 fuels as just carbons and hydrogens going into the reaction. So the next step is that I want to define my fuel in terms of number of moles. So the number of moles of my fuel is going to be equal to another numerical Python array. And this is going to be basically the ratio mixture of components of my fuel. So we haven't discussed this, or I haven't talked about this yet, but the mixture of my fuel, I already said, is a mixture of methane, ethane, and N-propane. But now I need to know the actual ratios of those. So I'm going to say that this fuel in this problem is going to be made up of 10 parts methane, 1.5 parts ethane, and 1 part N-propane. Okay, so now I have essentially determined the number of moles of my fuel, of 3 parts of my fuel. So the next step, I've determined the number of moles of fuel. Now I want to get more specific and determine the number of carbons and the number of moles of carbon and the number of moles of hydrogen in my fuel. So NC and NH are going to be equal to the number of moles of fuel at the number of carbons and hydrogen in my equation. So it's going to be N fuel at fuel CH of my equation. There we go. So that was the most difficult part of understanding the number of moles of carbons and hydrogens. Now I need to understand the number of moles of CO2, the number of moles of water, the number of moles of all the different other elemental components of the system. So I'm going to start with the number of moles of CO2 has to equal something. I need to tell my script that the number of moles of CO2 in my balanced equations is equal to a certain number. Well, I know that when I was doing my balances on the whiteboard earlier, that the number of moles of CO2 on the effluent side of the system were directly related to the number of moles of fuel, or the number of carbons in the fuel going into the system. So the number of number of moles of CO2 is going to be equal to the number of moles of carbon. I'm also going to need to figure out the number of moles of water, so H2O, and I know that the number of moles of H2O in the right-hand side of the equations that I balanced was directly determined on the number of hydrogens and oxygens on the left-hand side of the equations I balanced. So the number of H2O is going to be equal to, specifically, the number of hydrogens on the left side of the equation divided by 2. Next step, determine the number of moles of oxygen, so O2 in my equation. So that's on the left-hand side of my equation going into the system, and that's going to be directly related to the 79 to 21% ratio of nitrogen, and also it's going to be related to the H2O. So this is going to be related equal to the number of moles of carbon plus the number of moles of H2O divided by 2 in my system. Oops, not ready yet. And then the last element that I need to clarify the amount of is my nitrogen. So nitrogen doesn't react, and it's just part of the air that's going into the equation. But we know that the ratio has to be 79 over 21 in comparison to our number of moles of oxygen. So times N of O2. There we go. So I've defined the number of moles of all of the inputs and outputs chemically in my system. So the next step is that I need to combine these into a combination array. So my ins, my outs, my feed versus my effluent of my system. So the number of moles feeding into my system is going to be equal to a congregation of arrays that I've already set up. So I'm going to be using the numerical Python concatenate tool to combine a number of arrays together. So this is going to be np concatenate of numerical Python. What is this going to be? So my feed is a mixture of the fuel going into my system as well as the air or the oxygen and nitrogen going into my system. So this is going to be n underscore fuel, comma, and it's also going to be array so it's going to be a mixture of the number of moles of my fuel as well as a certain amount of oxygen and nitrogen, but no amounts of CO2 and H2O. So I'm going to call this numerical Python array of, we're going to have some number of moles of oxygen, some number of moles of nitrogen. I'm not going to have any moles of water, and I'm not going to have any moles of CO2. And that should make up the combined array for my feed going into the system. So now I need to set up the combined array of moles coming out of my system, so my effluent. So this will be, again, another np concatenate of fuel and elements leaving the system. But this time, there isn't any fuel exiting the system. All the fuel is being spent up in the process of burning the fuel. So, and it actually becomes the CO2 in the water. So in order to tell my script that I'm not going to have any fuel and that array is going to go to 0, so my methane, my ethane, and my N-propane are going to go to 0, I'm going to be using the numerical Python like zeros like N fuel. So what this will do is it will make an identical array to the array N fuel and make everything equal to 0 because all of the fuel in that array was spent in the reaction. And then np.array of my chemical components. Now, I'm not going to have any oxygen, so that's going to be 0. That's going to be spent up in the reaction and turned into CO2 and water. I'm still going to have nitrogen, so that will still be N2. And now I will have, instead of 0 and 0 for my CO2 and water, I will have N of CO2 and then N of H2O. There we go. So I've set up my combined arrays for the input to my system and the combined arrays of the output of my system. So the only thing left to do is to define the energy balance and solve for the temperature. So if I define my energy balance with respect to, let's say, vector, call it V, and my vector that I'm looking for is actually my temperature, so this will be T equals V. Return. Now I can determine the difference between the enthalpy of the ideal gas at the initial temperature of 298 Kelvin versus the final temperature that we're looking for. So this will be enthalpy of the ideal gas of my feed, and it's coming in at a temperature of 298 Kelvin, minus the enthalpy of the ideal gas of the effluent, so N effluent, at a temperature T that I do not know. So the only thing left to do is find out what that temperature is. So using the root function of my energy balance, and it's going to ask me for an initial guess. So let's say that the final temperature is 3000, but we don't know that. Let's see what it tells us. Okay. So it's told me that my X value final is 0.0344, which doesn't seem right. Okay. Let's see if I've made a mistake anywhere. Hmm. I'm going to pause this and come back and hopefully be able to find my mistake. So I was able to find my mistake, and it was quite simple. The number of nitrogens is actually correspondent to the number of uh, moles of H2O on the right-hand side of the system. So I'm going to try running this all again. Hopefully I get a better looking answer. Oh, nope, still wrong. So what else could it be? One moment. Sorry about that, I'm back. So I went back through and I did a little bit of looking into my code, and I realized that it was just a simple parentheses bracket error up here when I defined the number of moles of my feed and the number of moles of my effluent. For some reason that was giving me the wrong answer. So I reran it, and now I have 1218 degrees Kelvin as my final adiabatic flame temperature. So thank you very much for watching. I apologize for the issue there at the end, but I was able to get it all to work. So I was able to start with my system at an adiabatic flame temperature of a steady state system, and given that a mixture of fuel of methane and propane and ethane were brought into a 10 to 1.5 to 1 ratio, mixed that with air, which was 79% nitrogen and 21% oxygen, a flame was produced, generating CO2 and water. And given that the starting temperature was 298 Kelvin, the final temperature of the adiabatic flame is 1218 degrees Kelvin. So another error that I just realized that I encountered was that here when I'm defining the number of moles of the oxygen within my system, it is actually the number of moles of carbon plus the number of moles of H2O divided by 2. I originally had this with both of these divided by 2, but it's only the number of moles of H2O divided by 2 in the right-hand side of my solution. And by doing this, it actually changed my answer, and the final temperature is 875 degrees Kelvin. So I wanted to add that in there. Thank you.